last class we have learned about the body wave, right? PNS wave, and when there is a boundary condition, then you have a surface wave or the different mode. So body wave assumes that you have an infinite medium, right? So it's kind of a plane stress and condition. And when you have a boundary, as soon as you have a boundary, you have Rayleigh wave, surface wave, or the lobe wave, or if it has a beam type, then you have also Lamb wave. And what else? We have also see the effect of the interface. You have a different medium with a different mechanical impedance, then you have a reflection and a refraction, right? And the angle of the reflective wave and the reflective wave is what that follows the Snell's law, right? So I think we have covered that. And what else? And the reflection coefficient and the refraction coefficient, that is function of the impedance, right? Z1, Z2, I think if you remember that. And what's the definition of the impedance? Remember? Rho times V, the density times velocity, right? That gives you the impedance. So if there's an impedance mismatch, so that you have a large difference in impedance, then you will have higher reflection, and if the impedance are similar to each other, then you have more transmission, right? Then is that all? 그다음에 뭐 있지? There's one more. Reflection 다음에 뭐 하나 있었는데. 뭐였니? Reflection. 그게 다였나? Reflection까지가 다였나 보다. Oh, yes. Okay. So then, so now we are relaxing the homogeneity. So this means that you have a dispersion. So dispersion means when you have a one frequency of wave propagating, then in the end you have a range of the frequency. So the frequency shifts during the propagation, right? And also during that propagation you have energy loss. So we are now talking about the lossy media and intrinsic material loss. So whenever you have a material and you are applying the energy there, and the energy will propagate, but at some point it will attenuate and you don't get any energy, right? So that's the energy attenuation, and that happens in the wave propagation too. And in general, the rock, let me use this pen. The rock or the particulate material, the soil, is low, has a low attenuation, right? So it's called a low loss material, and this elastic modulus can be replaced by a complex modulus. So from now it's not anymore just the scalar or just real value. It has the different. You also have the two modulus. So for example, when we talk about the P wave, instead of the just constant modulus m, you have a m star, right? And this m star is m star is m real plus imaginary number and m2 prime, double prime. Right? So this is the storage modulus and this is the loss modulus. And if we solve this equation, we get the particle motion of the material. And before it was just a kappa, right? And now instead of a kappa, we have a gamma star. And gamma star is kappa minus I times alpha. So we have new parameter introduced, that is the alpha. Right? 안 보이니? Is it now better? 저기 안 좋아서 그래. 좀 앞으로 보십시오. 뒤에 있는 사람들 좀 앞으로 와도 됩니다. 안 보이니? 이퀘이션이 너무 작아서? So you guys can come a bit more to see better. So that projector has been old, I think. So here the attenuation is defined as the amplitude over the initial amplitude equals to epsilon to the minus alpha x. Right? So here you can see that it's the spatial scale, so it's not the time scale. So let's move on. The complex phase velocity, here you have a phase velocity, right? The Vp. So actually you can replace it with shear modulus. Then you get the shear velocity, right? Or the complex shear velocity. So you can apply the same formula to the shear mode too. So here I'm just using the P wave mode as a representative for the body wave. See omega over gamma star, and this is the definition. And if we get the real velocity, it's called the real phase velocity. So then following this equation, you get this, end up with this equation. And because we are talking about the small loss or the low loss, material, so then you get the simplified version, the constant modulus over density, the square root of the constant modulus of over density. And what about the attenuation? So here you have alpha, and if you derive the equation, then you get this final value. So omega, the angular frequency times tangent delta, over 2 times of P wave velocity. So these are derived from the definition. And if you look at closely, this tells you the real value tells you the phase velocity. So phase velocity means the velocity of a certain frequency, and the imaginary value tells you the attenuation. And when you look at here, this equation, the alpha, the attenuation coefficient, is function of omega and also the velocity, right? So as you're looking at the higher frequency, as the omega increases, what happens to alpha? Alpha also increases, right? So that means at higher frequency, you have higher attenuation for the same material, right? So for example, you are now generating a packet of wavelet, and then at a certain distance, the higher frequency will die first, right? So high frequency, and the low frequency still remains. Right? And what else? The Vp tells you that the stiff material has the low damping or the low attenuation. Right? So it's the same. The high frequency wave attenuates faster than the low frequency wave. So it's just description, and you can see from the equation too. So the shape of the propagating wavelet becomes wider with distance. For example, if the initial wave is like this is the frequency and the power spectrum. And as time goes by, or as the wave propagates, it becomes wider like this. Okay, question? Delta, because delta means the phase shift. It's mathematically convenient to use the phase shift. So there are so many different definitions regarding to the damping coefficient and the attenuation. We'll see it in a minute. So the parameters used to quantify the intrinsic material loss. So we use several engineering property or the parameters to describe the material attenuation, the intrinsic, the energy loss, and we can get the damping from resonant frequency, right? The FFRC or free vibration decay. So for example, you have a material and you measure the vibration while it decays. So you just maybe drop a ball, then you measure the vibration, and it's gonna go down. Eventually, it will die, right? And you measure the vibration, then you get the decay curve, and from there you can get the attenuation. Or you can apply some cycling loading, like here. Where is it? Like this one. So you can apply the cyclic loading and you get the stress and strain curve, and from the loop you can calculate the energy loss. Right? So if we assume the single degree of freedom system, I think this definition is familiar from the structural dynamics, right? And if the damping is larger than 1, it's over-damped system. And if damping is 1, critically damped system, and under-damped system if the damping is less than 1. Right? And from the loop, if you take in the soil dynamics, I think it looks familiar, right? So the delta W is the work done. So this is the area inside this blue circle. So it's the area of it's not circle, but the area of the circle. And here, this is the applied energy, okay? Work done by the external loading piston. So you can get the damping, and also, as I told you before, you can get the logarithmic decrement from the free vibration decay. So here the delta is the another term to describe the attenuation or the intrinsic material loss. And natural logarithm, before that, no, that's fine. So this delta is defined as this equation. So here, for example, here is the yi max. And the next cycle is here, right? After next cycle, this is yi plus 1 max. So this is energy loss per cycle. And quality factor is another term and defined as the the imaginary part of the modulus over the real part of the modulus. And also same is the tangent delta, and you can mathematically derive that this quality factor is equal to 2 times damping coefficient. And we can also define the skin depth. Skin depth is a penetration depth of a wave into material that causes 1 over E decay in amplitude. So, for example, this is A naught. Here. And this is skin depth. So by definition, the amplitude decays to 1 over E times the initial amplitude. Then this X tells you the skin depth. So that means that, for example, if the skin depth is 1 meter, at the 1 meter, your amplitude is reduced by 1 over E. So 1 over E is how much is it? 1 divided by 2.7, about 35. So 65 has already died. So can we derive the skin depth from this equation to relate with the alpha? Let's do that. A and A will cancel out. Cancel out. Alpha X 1 over E, and then this is what, minus 1, so that's minus alpha X minus C. So X is, the skin depth is defined as 1 over alpha. Right? Let's think about the unit. What would be the unit of the alpha? Unit alpha. One over meter? Oh, so 1 over length, right? So it could be 1 over meter, or 1 over centimeter, or 1 over millimeter. Right? So the relations between attenuation coefficient. Here, the delta, the logarithmic decrement is 2 pi d, and alpha t times t, alpha x times lambda, 1 over q. So there are so many different parameters, right? You have a d, and you have delta, and you have alpha, and you have q, right? So alpha t is, let's think about this one. Where is it? Here. Good. Let's think about the free vibration decay. This goes like this. And the delta is ln y over y. Right? Or you can use the A, right? Amplitude. And if this is a spatial scale, then this y is y0 e minus alpha x. Here the alpha is the special scale attenuation coefficient. So this one in space. And how does this alpha and the delta will correlate? Because it has moved by how much? Lambda, right? So the wavelength is lambda. So if you put the lambda minus alpha lambda is same with the delta. Oh, sorry, minus delta. So the alpha is delta over lambda. Alpha x. Sorry about the very messy note. I'm getting used to it. And if you change it to time scale, instead of the lambda, what's the it's period, right? For the one cycle. For one cycle, you have a period t, so the alpha t is delta over t. So here, attenuation coefficient in time, so use the t, and this one use the lambda, and d, damping coefficient is the energy dissipated, the energy loss per radian, so we can multiply 2 pi, so that's why we are multiplying 2 pi here. Right? If you multiply 2 pi, it becomes the one cycle. Right? And yeah, delta is the energy loss per cycle. And when people say the alpha as an attenuation coefficient is generally the attenuation in space. Where is the alpha here? Yeah, this one is the same with the alpha x. Can you move on? So just remember the definition, and that there are correlation among these parameters. So then besides the material intrinsic loss, you can have a geometric spreading. So as I told you that when there's a spherical wavefront, the energy will attenuate because the spherical wavefront becomes larger, right? So that's gonna be, so amplitude times the area of the front will remain the constant. So that as the area becomes larger, the A amplitude will decrease. So you have a geometric attenuation, and you have a material loss, and when there's some interface, then you have a transmission reflection. So that's why also from there you lose some energy, right? Apparent attenuation. So this is from scattering. Interface. And ultimately the energy is dissipated in the form of heat and radiated in emissions or observed in phase transformations. So this is the total attenuation. So whenever you have an energy propagation, there will be 3 components that can attenuate the energy: the geometric spreading, material loss, and apparent attenuation. Then let's look at the geometric spreading. Geometric spreading is a decreasing wave amplitude with distance due to an increase in size of the surface front, and this amplitude is proportional to square root r, reciprocal of the square root r, right? And then you have this relation A amplitude A2 over A1 is R1 over R2 to the this exponent, and this exponent can change depending on the shape of the front. When you have a spherical front, you have a 1, and cylindrical front, 0.5, and plane wave, you don't have any geometric spreading. So plane wave means that you have PNS wave in the infinite medium. And these are the solution for the plane waves and spherical waves. And I think we can skip this one. We have seen this one before. And material loss, material damping, internal damping, intrinsic attenuation is all the same. And people use different parameters or the terminology. And if material losses are modeled as an exponential decay, the amplitude at location 2 is related to the amplitude at location 1 as this equation. And so this alpha is the attenuation coefficient in space. Right? So we've seen this one a lot. And there is a apparent attenuation, partial transmission, and mode conversion at the interface. So when you have 4, wave coming in, we have wave 2. This is transmission coefficient times A1, and you have a reflective wave, right? AR, R times A1. This is media wave 1 and medium 2. Right? So the total attenuation is the sum of geometric spreading and material intrinsic loss and the apparent attenuation. So here you can see that the amplitude change A1 over A2 is for geometric spreading times material loss times the apparent loss. So for example, this is the source, and when there's a wave and this location at R1, this is the source, sorry. 어떻게 지우지? So here the amplitude is A1, here is amplitude is A2. Then if you know the geometric spreading coefficient, so let's say that this is the surface wave, then this exponent, this wiggle will be 0.5, and you know the distance R1 and R2. Then, and this is homogeneous medium, so the T will be just 1. And you can calculate the alpha, right? So that's the way you calculate the attenuation from the surface wave survey, the SASW. So then let's do some calculation. Express the total attenuation A1 over A2 in decibel notation. And the decibel notation is defined as this 20 times log A1 over A2. And you can derive the total decibel attenuation in terms of geometric spreading and what? Material intrinsic loss and the apparent attenuation. Okay, let me show the final equation first. So the equation will look like this one, right? So this is a log base 10, R2 over R1 plus 27 times R2 minus R1 Q lambda. So the alpha, I think the alpha is correlated with the Q with this Q. Mm-hmm. That's true. Alpha is pi f over qv, and v is f lambda. So if you put that in here, then pi over q lambda. So where's pi? I think it's already in here. 27 also already includes the pi. Right? Okay, then let's put the numbers in here. 한 사람, anyone have the value? Total attenuation. Okay, let's do the apparent attenuation. Here, t is 1, so it's just 0, right? So if we put the values here, 1, then this term goes to 0. So you have only geometric damping and the material loss. So dB attenuation is dB geometry and dB loss, and dB loss is what? 27 times R2 minus R1 is 5 lambda over Q is 50 times lambda. Then how much is it? Lambda will cancel out. 10, so this is about 2.5, 2.7, and dB attenuation, the geometry is 20 times, this is spherical spreading, so how much is this wiggle, the exponent? It's 1, right? And log R2 is 2R1, so E R1 over R1. And how much is it? 20 times log 2, then 6.02? 그런가? That's good. And dB apparent is 0. Right? So the total attenuation is about 8.7. So you can see that for the spherical spreading, this one, right? The geometric spreading is much larger than the material loss. Right? Material loss, intrinsic loss is only 2.7, and here 6.2. So if you think about the amplitude, then this is the exponent to the base 10. So 10 to the 2.7 and 10 to the 6. So difference will be really big, right? Does it make sense? So geometric spreading is the one that makes the attenuation measurement difficult, right? In the field test, it's very difficult because of this geometric spreading. But in the laboratory test, because you can define the geometry of the sample, and you can eliminate this geometric spreading, so then you get only the material damping. So then you have more low noise measurement. 질문 있니? 질문이요? Good. So then we'll talk about the dispersive media, and dispersion means that the velocity varies with frequency. Okay? And if the phase velocity decreases with frequency, it's called a normal dispersion. And if phase velocity increases with frequency, it's an anomalous dispersion. It's just the common language in the geophysics and also the electromagnetism. And waves are rarely perfectly monochromatic. So that means monochromatic means that it has only one frequency. But instead of have a finite bandwidth centered around some mean frequency wave group. Right? So in general, when you generate the wave, you cannot generate one frequency wave. You have a packet of frequency. Right? Frequency in a wave packet is assumed only slightly different. So for example, here, the red one is at 60 Hertz, and the blue one is at 55 Hertz. And when you combine these two, you have this kind of a modulation. Right? So you have a modulating wave, and also there's a carrier wave. Right? So, and superposition of two equal amplitude traveling disturbances is this. So U naught, and the first term is for the one frequency, W1, the omega 1, sorry. And the second term is for the second wave packet, is omega 2. And you can superimpose each other. And the phase velocity, and using this trigonometric relation, you can get this final equation. And here you have a average of the omega, the angular frequency, and the difference of the angular frequency. And here the low frequency term, the one with the delta omega, here this term is called the modulation term, and the one with the higher frequency is called the carrier term. So the low frequency is modulation and carrier, higher frequency carrier term, and here is telling you the group velocity, and here each phase tells you the phase velocity. I think So the group velocity is the limit of the modulation velocity. So when this wave number goes to 0, you have a d omega over d kappa, and this is the slope of this angular frequency versus wave number graph. So I think this will give you more explanation. When a wave contains a narrow band of frequency, or if it's not strongly dispersive, its propagation can be adequately described by the corresponding group velocity. So the group velocity is the velocity of the energy propagation. So that represents the whole wave packet. And the propagation velocity of the wide band disturbance in a dispersive media cannot be characterized by any single group velocity. Summary, the phase velocity is the velocity at which the wavefronts of a pure frequency tone travel, and group velocity is the velocity of the wave packet, which are made up of a range of spectral components travel. So just be aware of there's a difference in phase velocity and group velocity. And you can also, when you have measurement of the acoustic signal, and you can do the Fourier transform, and you can divide it into each frequency band, and you get the phase velocity of each frequency band. I think this is the duplication of the previous slides. So this L is the longitudinal mode. So it's a function of the Young's modulus, and Vs is the Gs. So the Poisson's ratio is 1/2, and a function of the longitudinal wave velocity and the shear wave velocity. And P wave and the Vs also can be related with this Poisson's ratio. And velocity ratio defined as this one. So you can see that the Poisson's ratio will determine the ratio between the P and S wave. Here also the Rayleigh wave and the shear wave. And if we plot it here versus the Poisson's ratio, the P wave over the shear wave, so shear wave is the reference wave velocity. P wave increases as the Poisson's ratio increases, and also the Rayleigh wave increases with the Poisson's ratio increase. So when the Poisson's ratio is 0, then P wave is about 1.4 times larger than the shear wave, and when it goes to 0.5, this goes to infinite. And the shear wave here 0.7, the Rayleigh wave is about 0.87, and here 0.95. So you get the idea about the P wave velocity and the Rayleigh wave velocity.
그러면은 포화성비가 포화된 정도에서는 0.5인데 좀 BP가 그때는 엄청 커진다는 얘기죠.
So it's not perfectly 0.5, but the ratio becomes really high. So BP over BS increases as the saturation increases. Good point. Okay. So actually, that leads to this relation here. When you have a low BP over BS relation, so the partially saturated sand or partially saturated rock, the QS and QL, in terms of the magnitude, QS is largest and the QP is the smallest. So that means what? The attenuation, P wave attenuation is much larger than the shear wave attenuation, right? Attenuation is alpha is 1/Q. Right? And in case of the high BP over BS material, for example, if it's fully saturated case, then it's going to be the other way. So 1/QP, so P wave attenuation is smallest one, and the S wave attenuation is the largest one. And the Rayleigh wave attenuation can be also related to the attenuation of the body wave mathematically using the elasticity. So now we're going to relax the isotropy. So far we have seen the isotropic material, the elastic wave propagation in isotropic material. And let's use this one. Yep. in the 2D element, we have shear stress component and the axial stress, sigma x and sigma y, right? And in 3D element, we have sigma x, sigma y, sigma z, and tau xy, tau yz, and tau xz, right? So we have a 6 component. Then sigma is what? Some elastic modulus or the stiffness matrix times strain, right? So this is what? You have a 6 indexes, so this has to be 6 by 6, and this is strain. So in total, you can have, because the tau xy is the same with tau yx, so then you have 6 components. And when you look at the constitutive equation, so using this stress-strain relation, so this is from the Hooke's law, right? And because we have a 1, 2, 3 dimension, or the x, y, z, if you look at the 3D stress distribution, then we have a 9 component, but because of the symmetry, we have only 6 stress component, so that stiffness will have the 6 by 6, 36 component, but because of the symmetry here, where is it? This one will be the same with this one. So we get 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, and you have total 21 component. So to describe the anisotropy in the 3D material, you need a 21 stiffness parameter. Right? That's a lot. But in general, we just only use the one, right? One parameter, Young's modulus. That's it, right? And when we say the Young's modulus, just one parameter, it's a homogeneous and the isotropic material. And orthotropic has at least 2 orthogonal planes of symmetry, and here you have a 9 independent elastic constant, and here elastic moduli Ex, Ey, Ez, Gxy, Gyz, Ggx, and Poisson's ratio. And when you look at the stiffness matrix, here X, Young's modulus Ex, Ey, Ez, and Gxy, Gyz, Ggx, and also the Poisson's ratio. And in the soil mechanics and also the geology, the resource engineering, we generally use this assumption, transverse isotropic. So that means that you have a different layer or the different stiffness with the z-axis. So as you go deeper, in general, you have a higher strength, right? So, or the higher stiffness. So this is called a cross-anisotropy. But in the plane wise, the x and y axis are all the symmetry, right? So it's kind of a axis symmetry condition. Transverse isotropic, so in this case 5 independent elastic constant, and here the the Young's modulus S and T, so that's the x and y axis, are the same. So then 5 independent variables. So to summary, anisotropic, you have how many variables? 21, right? And here you have 9 and 5, and isotropic you have 2 variables, E and G. All the Young's-Mills and Poisson's ratio. Okay, in the cross-anisotropy, again it's the same. C11, C12, C13, and C33 and C44. I think this is the same with the previous stiffness matrix. And here, I think equation is just equation, and you need to look at this terminology. Pure shear mode for the SH wave. So SH is polarized in horizontal direction, right? And SH wave, because in every direction in the plane you have same stiffness, so you get the pure shear mode. But if it's polarized in vertical direction, the upper stiffness, the upside one and the downside one is different. You have a difference in stiffness, so that you don't get the pure shear wave. It's gonna be somehow in between. It could be inclinated, right? Or it could be some of the mixture of the body wave, P wave. So that's why we call it the quasi shear mode. And quasi longitudinal mode is also the P wave in one direction. So in cross-anisotropy, you get pure shear mode, and quasi shear mode, and quasi longitudinal mode. And anisotropy and the depth-dependent stiffness. This is important because the stiffness is controlled by the effective stress. Effective stress. And stiffness increases with depth. So for example, the shear stiffness is what? Is increases with the vertical effective stress. So the stiffness and Z may increase in linearly, or it could be non-linearly increase like this. And gradual change in stiffness causes continuous reflection and leads to curved ray. And Fermat's principle, the ray travels on the path that minimizes the travel time between 2 points. So let's assume that we have a gradually heterogeneous weakly anisotropic medium, so that the, for example, the wave velocity increases with the depth linearly. So this is V. See? And if we have a source here, and here the receiver, because they are, maybe you can assume that this goes to straight like this, but the lower part has a higher velocity, so this might be faster curved ray may be faster than the straight ray, right? Because of the higher velocity in the deeper region. And here, theta is, this is the theta. So for example, if ray goes to this direction, sorry about that, the theta is here. Source. And then the equation of the ray path from source to receiver can be derived as this equation, and this is the homework to derive this equation. The analytical expression for the ray path can be derived for simple velocity field. I think let me explain the next slide first. So in this heterogeneous or the cross-anisotropic material, when you have a source here and receiver here, solid, so this red one gives you the faster arrival time than the straight ray. So that you can draw the ray path using this equation. So this x, as ray goes to x, the horizontal direction, you can calculate the depth z using these two parameters, b and the velocity of the so receiver location and source location, and what else? A and B is the, I think that's the velocity profile with depth, and C is the anisotropy. And when you have, so this is isotropic material, so the horizontal velocity is the same with the vertical velocity, and the dotted line is when you have vertical velocity larger than the horizontal velocity, right? So what's the definition of the C? C is vertical velocity over the horizontal velocity. Right? So when you have a anisotropic medium like this, then because the vertical is more faster, so that you have a more curved ray than the isotropic medium. So to derive this equation, actually I've been trying to derive this equation yesterday, but I failed it. So I hope you can solve it for me. Analytical expression for the ray path can be derived for simple velocity field. The main idea is to write an expression for the travel time in terms of the field parameter. And then, so to find the minimum travel time, you set the derivative to 0 to find the ray path that renders the minimum travel time. And variation of velocity with the inclination q, or the theta here, of the ray is a piecewise elliptical. So that's this equation. Right? The v theta is the vertical velocity times this some parameter as a function of the theta. And I think they use this calculus of variation and Fermat and the Snell's law to derive this equation. So the hint is to use these three principles. Good question so far? No? So now we are relaxing the linear elasticity. If the variation of the stiffness with the strain is positive, stiffness increases with strain and the subsequent disturbance travels at a faster velocity than the original one, stiffening the shape of the front of the pulse, leading to shock wave and stretching the rarefaction cycle. So that when the strain is large enough, then you have a stiffening the effect on the material, so that you have a distortion in the rarefaction here. So final comment is the summary of this chapter. Let's see, PNS wave in the infinite medium and free boundary for the Rayleigh mode and the Rod wave, heterogeneity for the ray bending, and attenuation, and also the intrinsic material loss, intrinsic loss, energy loss, Anisotropy. Okay, good. I think that's all. So chapter 6 is a very fundamental and theoretical part. And chapter 7 is also another fundamental theory, but that will deal with the soil and the rock with the pore fluid more.